All right. Good morning, folks. I hope everyone had a good weekend. Hopefully you're able to get outside for a little bit and enjoy our weather. But I would like to continue on with where we left off on Friday, and we need to get done with liquids today, and we will get done with liquids today. Hopefully we can get started with the solids. I'll wrap up with the solids tomorrow, and then we'll start the gas chapter. Okay, so chapter 14. What I decided to do is that we'll hold off on meeting together until after the AP exams. Maybe this Friday. It doesn't look like anyone's taking any APs on Thursday or Friday. So let me know if you are, and that way then I'll try to reschedule our meeting, our Zoom meet date for next week. But it looks like this Friday we'll be able to meet on Friday, a live Zoom meeting just to kind of get caught up, see how you folks are doing, and then I'll talk about at that point then what we'll do to finish up the semester. Okay, so right now let's plan on meeting at on Friday at with our Zoom meeting. I'll post the Zoom meet information for you, and then we'll go ahead and we'll meet on Friday. Okay. All right, very good, folks. So, like I said, you don't. If you have any questions, don't wait till Friday. Stop by after school, any day after school, 1:30 to 2:30 on Zoom. It's the same. Basically, the information's the same. But if you don't have that information, just look on Classroom. But if you don't want to scroll through all that to find the information, just go ahead and email me a time that you want to meet, and then I'll respond, and I'll also give you the time, the information for the Zoom meet as well. Okay, the office hours. All right, so let's go ahead. Let's pick up where we left off with on Friday. We talked about vapor pressure. We finished up with that discussion. We talked about how vapor pressure is the pressure that's exerted by a liquid as it evaporates. So all liquids evaporate. They evaporate at different temperatures. They evaporate at different speeds. We saw that depending on the temperature as well. And then we saw then that each liquid has a unique vapor pressure that allows us to use vapor pressure to distinguish from one liquid to another. Okay, so vapor pressure is an important property of liquids, and that's something that we need to make sure we wrap our minds around. And that is, vapor pressure is a property that's associated with liquids and not of gases. And the problem, again, like I said, for many folks learning this, is that when we talk about vapor and pressure, we're thinking the pressure exerted by a gas, and so it's a property of gases. And so the answer there is no. Okay? Vapor pressure is a property that we use to distinguish liquids. Liquids will create this vapor pressure by evaporation. Okay? And so prior to talking about vapor pressure, we talked about evaporation, and we were able to describe evaporation. We were able to describe vapor pressure on both the macroscopic scale and on the microscopic scale. And you got to make sure you keep that in mind as we move forward, because when we start talking about boiling here, okay, when we start talking about boiling, we're going to incorporate both what we know about vapor pressure and its dependence on temperature. Okay? And we're going to use that in order to discuss what boiling is, and we're going to contrast what boiling is versus evaporation. Okay, and so that's where I want to start out with here. Okay, so on the macroscopic scale, that is what the events that we can observe with both boiling and with evaporation, and that's what you see on this screen here. We need to be able to distinguish between the two of them. We can describe the similarities, and I'll go ahead and I'll do that. But we need to be able to distinguish between the two of them, and then be able to explain that difference based upon the behavior of the particles. Okay. All right. So first of all, let's compare them. Both vaporization, both evaporation and boiling, both of them are processes that we refer to as vaporizing. So both are vaporization processes. Okay, so we'll write that here. We'll write that here as well, which means then both involve vaporization. Both of them involve taking a liquid and transforming it into a gas. So both of these processes are vaporization. Okay, so they both involve taking a liquid and transforming it into a gas. Okay? All right. With that said, then both of these also, let's go ahead and list this in, are linked to temperature. temperature dependent. Okay, so that's temperature dependent. Okay, and this is also temperature dependent. Both of them, with changing temperature, the process will change. Okay. All right. Now that's how they're the same, and then there are other similarities that we'll go over when the time comes. Okay, but there's a key difference. I'm sorry. Well, only one more. Okay, so we see that with both of these here, the liquid level decreases. Okay, and here, liquid level decreases as well. Okay, so we can observe a drop in the liquid level as this happens. Okay. All right, so they are both processes that involve vaporization. They both are temperature dependent. They both we both can just see then with both of these, we can see a drop in the liquid level as well. Okay. All right, so with that said, then let's highlight a key difference here when it comes to this. Okay, so with evaporation, the vaporization occurs at the surface. Okay. Which means then the process by which a liquid becomes a gas, that only occurs at the surface. Okay. For the boiling, for the process of boiling, okay, vaporization occurs throughout the liquid. And that, folks, is going to be the key difference that we can observe about boiling versus evaporation. So let me explain here, okay? So what happens here then, and we talked about this, as you increase the temperature, and so let's go ahead and let's explain this last part here, this last difference, this last characterization, and this last comparison of boiling versus evaporation on a microscopic level. Okay? So we know then, we said then that as you increase the temperature on a liquid, okay, the particles start to move faster. Okay, so the particles start to move faster. So we can go ahead then and we can write this down. We can see this here. The particles start to move faster. So let's go ahead and highlight a few particles here. Okay, so we have particles here at the surface and underneath the surface. Okay, we said then that these particles, liquid particles, are in constant motion. They are always moving around. Okay, they are moving in a random, rapid, and constant manner, like we said earlier as we characterized liquids. But the key difference between liquids and gases is that they have these interactions, these attractions for one another, okay, that they are attracted to one another, so that then the particles at the surface here and every particle, they are bound together. They are kind of attracted to every other particle around them. So as they move around, they have these interactions and these attractions to one another as well. Okay? So as you increase the temperature, they start moving faster and faster, and that's true for all of the particles. And we talked about this. So remember, as you increase the temperature, you increase the average kinetic energy for all the particles. Okay? Which means then the particles at the surface here are moving faster and faster as well. Some of these particles then will eventually pick up enough speed, they will have enough kinetic energy where they will break free of these attractions. That means then what happens is that they will break this attraction here, this one will break the attraction there, and because there's nothing holding it down anymore, nothing holding down this particle anymore, it just flies off into the space above it, thus becoming a gas. Excuse me. And so that's the process of which we call evaporation. And so that only happens at the surface. Only the particles at the surface now are moving fast enough in order to break free. Okay. Once this particle breaks free, another particle comes in, fills in this space, waits its turn, picks up more kinetic energy, and then it vaporizes as well. Okay. Let's shift to the boiling here. Okay. So as you start to increase the temperature more and more and more, okay, and so as you increase the temperature more and more and more, these particles here, let's go ahead and focus in on these particles here. Okay. What happens then is these particles move, okay, as you increase the temperature, they move faster and faster. And so all these particles here start moving faster and faster and faster, just like with the process by which we call evaporation. Okay? Now, at some point then, if you continue to increase the temperature, as you increase the temperature, and let's make sure we keep this in mind here, as you increase the temperature, these particles here they will start moving so fast. They will begin moving so fast that what happens is that all the particles now, and we can start erasing this in, all of these particles now start to break these attractions. And as they break these attractions, just like what we said with evaporation, if those attractions for one another is broken, now they've become a gas. Remember, what distinguishes a liquid from a gas is that liquid particles have these attractions from one another. And so if these attractions are broken, not only at the surface here, but underneath the surface as well, you're going to get then gas particles forming. Gas particles forming underneath the surface. That means then the liquid particles here, they vaporize not only at the surface, like with evaporation, but they will also vaporize underneath the surface. And those, folks, are the bubbles that we see. And so the bubbles that we see at the bottom, okay, the bubbles that we see that are rising up from the bottom of underneath the liquid, those are liquid particles that have become vaporized. Okay? Those are not air particles. Those are not air bubbles, folks. Those are vapor particles. Those are vapor bubbles that are coming up. So if it's water, those are water vapors. If it's ethanol, those are ethanol vapors that are rising up to the top and breaking free and joining and then becoming a vapor up here. Okay? All right, so that's boiling. Okay? And so that's what we can observe. We can observe the bubbles here, but we don't have any bubbles here. So bubbles don't form here, so no bubbles here, okay, because the process of vaporization only occurs at the surface. Bubbles here because you have vaporization occurring throughout the liquid. So you have vapor particles forming underneath the surface, and that's how we account for the those bubbles. Okay, all right. So that's the key difference between boiling and vaporization, both on a macroscopic level, bubbles versus no bubbles, and on a microscopic level, where you have particles underneath the surface, not just on the surface, that are acquiring enough kinetic energy to break free. Okay? Now that's only if you continue to increase the temperature up to this temperature that we call the boiling point. Okay? And so last thing I want to do is I want to make sure you understand then that when a liquid is boiling, it is still evaporating at the same time. Okay? That means the particles at the surface are still breaking free. That's how we define evaporation. So therefore, when a liquid boils, it also continues to evaporate. It doesn't stop evaporating. It's not boiling or evaporation at that point. It's both. Now, evaporation occurs without boiling, but when boiling occurs, evaporation also still occurs. Okay? All right, so I want you to make sure you keep that in mind. Okay? All right, so with that said then, that's how we can explain it. Okay, that's how we explain it. But the last part of this statement over, which I want to point out to you, which we're going to start with right now, okay, and that is, we're saying here then that the pressure, the vapor pressure here, okay, can overcome the atmospheric pressure. Now, what does that mean? And how does that relate to the definition of boiling that we give down here? Okay. All right, so let's take a look at that definition of boiling that we're going to use moving forward. Okay, so we know what boiling looks like. We can explain what that boiling, how that boiling occurs on a microscope. We know what the particles are doing. Okay? So the way that we're going to define boiling then is it's going to be a temperature. Okay, so we're going to define boiling as a temperature, and the boiling point then as the temperature at which we see all this happen. We see the bubbles. Okay? We see the bubbles happening. So that's how we know we've reached this point that we call the boiling point. But the boiling point is going to be a temperature for a liquid. The temperature at which the liquid's vapor pressure is going to be equal to the pressure outside of it, the external pressure, which we call the environment. Okay? So you can imagine then that these gas particles here, so these are the gas particles from the liquid. They've escaped the liquid. Okay? And so what they do then is as they go up to the top here, they're going to run into particles that are already here. For example, if this is the air, we're going to have then particles that are floating around, gas particles that are floating around already. Okay? And so these gas particles, remember for air, for example, it's a mixture of gases. So these particles then could be water vapors. They could be oxygen, nitrogen, carbon dioxide. So there are already gas particles up here that are not vapor particles. These are gas particles that are part of the air. Let's keep that in mind. Okay? So they're floating around up here. They are in this space above the liquid. Okay? and they cannot move in and become part of the liquid. So they kind of just float around and they collide and they bounce into each other and everything else around them. We talked about gas particles moving in that manner. Okay? And so as they do so, they will also bounce up against the liquid. They're going to go in and they're going to collide against the liquid. And as they do so, they push down. They push down in the liquid. And now remember, unlike these particles here, unlike these blue particles that are vapor particles of the liquid, okay, these particles here, as they go down and they collide in with the liquid, they just become part of the liquid again. They form the attraction, they become part of the liquid again. However, these air particles here, and we'll just generically call these air particles. We won't specify that they're oxygen or nitrogen, but these air particles here, as they go in, they can't become part of the liquid. So what they do is, as they push in, as they collide with the surface of the liquid, they push down on the liquid. And as they push down on the liquid, they prevent these liquid particles here from leaving. So this is what we refer to as the external pressure. The external pressure is the pressure exerted by the air particles on top of the liquid pushing down on the liquid. Remember, we talked about that external pressure as atmospheric pressure. We can feel the air particles pushing down on us, that external pressure, that atmospheric pressure. We can feel it. And we talked about this early on when we talked about gases. And we saw then how as we move up in elevation, that external pressure decreases. But these gas particles, remember, these air particles here, they are pushing down on everything, which means then they're going to push down on this liquid as well. And as they push down on the liquid, they're going to try to limit the number of these liquid particles from evaporating, from vaporizing. Okay? And so what happens though, and this is where the definition of boiling comes in, folks. What happens though is that as you crank up the temperature on the liquid, as you turn up the temperature on the liquid, these particles here, they start moving so fast that these particles, the air particles, have a really hard time pushing down on them. And so these liquid particles here at the boiling point, bam, they just are able to break free, and these air particles are unable then to continue to push down and to keep those liquid particles in place. Okay, and so make sure you understand this. The way that we're defining boiling here allows us to explain the relationship between atmospheric pressure, vapor pressure, okay, and examine that on both a macroscopic and a microscopic level. Okay, so make sure you keep that in mind because that's going to be important, folks. Okay? And so if you need to review what atmospheric pressure is and how that relates to what atmospheric pressure is, you need to know that in order to understand how we can define then boiling here. Okay, so the boiling point is the temperature when the liquid, it has enough kinetic energy, okay, where all the particles at the liquid can break free, and become part of become a vapor. And they can become part of it because they have enough energy now to overcome not only the surface here, okay, the attractions here at the surface, but they can also overcome the attractions with each other, but they can also overcome the force in which these air particles are pushing down on them. Okay? And so that is how we define the boiling point. So let's go ahead and let's take a look at then how this works. So here it is. We have then, we recognize this graph. We've used this graph before, okay, and we've analyzed this graph before. We saw then that with this graph here, we have the pressure. This is vapor pressure now, okay, so this is vapor pressure that we're measuring. This is vapor pressure, okay, along the y-axis, okay, and the pressure here is in torr. I've given you here then that 760 torr is going to be equal to 1 atmosphere. Remember, 1 atmosphere is the pressure at sea level, the normal pressure at sea level. And then we have temperature on the bottom here. Okay? And we analyzed this graph here, and we saw then that as the temperature increases, the vapor pressure increases as well, because the evaporation increases. Okay? All right, so what I've done here is I've highlighted a few temperatures here for you. Let's take a look at dimethyl ether here first. So it's negative 123, negative 23 degrees Celsius. Okay, why do we do that? Well, let's go ahead. Negative 23 here. Let's go ahead and let's trace the line here. Negative 23, I think is about right here. Okay, so that's about negative 23 right there. Okay, so drawing that line right there, negative 23 degrees Celsius. Okay, let's go ahead and consider this here. negative 23 degrees Celsius, about right here. The pressure roughly, what, 750, and we'll call that 760 torr. Okay, so at that temperature, dimethyl ether reaches that point, which is about 760 torr. Okay, let's go ahead and do the same thing for benzene here. Okay, and I'll finish up this benzene. Let's trace this. So benzene at 80 degrees Celsius, which is around right here. Let's trace a line down. So at 80 degrees Celsius, about right there. Okay, 80 degrees Celsius. What do we notice? We notice then that the pressure at 80 degrees Celsius for benzene is 760 torr. Okay, let's do the same thing for water at 100 degrees Celsius. 100 degrees Celsius. Okay, let's trace this. So 100 degrees Celsius right here. Let's trace our line up. Okay, and what do we notice? At 100 degrees Celsius, the pressure, the vapor pressure now, these are the vapor pressures, folks. Okay, these are vapor pressures. The vapor pressure exerted by water is also 760 torr. And then finally, with phenol here, let's go ahead and about 180 to 180 degrees Celsius. Let's go ahead and do that. Trace it down right here. That's about 180 there. Okay. What do we notice? The pressure for phenol, the vapor pressure exerted by phenol as well, is 760 torr. Okay, so at each one of these are all different temperatures. So each liquid is exerting this exact same vapor pressure at these different temperatures. So dimethyl ether will exert a vapor pressure of 760 at negative 23 degrees Celsius. Benzene will exert that same vapor pressure, but at 80 degrees Celsius. Same thing with water. Water exerts that vapor pressure at 100 degrees Celsius, and phenol exerts that same vapor pressure, 760 torr here. Each one of these are exerting that vapor pressure at different temperatures. Okay? And so we've highlighted it here for you. Okay? Now, I've put in the box here for you that 760 torr is equal to 1 atmosphere. This is the atmospheric pressure. These are the vapor pressures. And make sure you keep this in mind. This is the vapor pressure exerted by water. This is the vapor pressure exerted by benzene at this temperature, and so forth. So these are the vapor pressures exerted by the liquid. And if you notice here, at each one of these temperatures, here, each liquid exerts the same vapor pressure as the atmospheric pressure. So at this temperature here, this is the temperature at which the liquid, in this case water, the water's vapor pressure is exactly equal to atmospheric pressure. These are, remember, the atmospheric pressure is exerted by the air particles. The vapor pressure is exerted by the particles of the liquid vaporizing. Okay? And so let me ask you to write this down. Okay, let me ask you to answer one question here for the lecture, and that is, okay, what's the significance of that temperature then? Okay? What happens with water at 100 degrees Celsius? Okay, and with that said, then relate your answer to what we just said here about vapor pressure and atmospheric pressure. So, what is the significance of the temperature of this 100 degrees Celsius for water? What do we know about that temperature? Okay, and then at that point, at that temperature, we know what happens. Okay, and so describe what happens at that temperature on the macroscopic level, and then using what we just talked about here, describe what's happening at the microscopic level. Okay, and make sure you include in your answer a reference to atmospheric pressure and this vapor pressure as well. Okay. All right. So very good, folks. Well, I was hoping that we could finish up with this, but that's all right. You know, I think it's important that you understand how we can explain a very important property of liquids. Okay, on both the microscopic and the macroscopic level. Again, that's a very important skill to be able to obtain. Okay. All right. So we'll pick up with this discussion tomorrow. Please make sure you write down your answer, a few sentences. Make sure then that you submit that work, and then I'll have it for tomorrow, and then we'll compare answers tomorrow. Okay. All right, folks. Very good. Have a good day, and I will see you tomorrow.